All right, today another exciting eddy current video. I'll be testing some protruding fasteners on multi-layered aircraft panels. You can see the top side has flush mounted fasteners. I would be using a slide probe for those in another video, but today we're going to focus on raised fasteners. And here you on the right hand side of the screen you can see an EDM notch coming away from a fastener, as they often do. There's probably a few more in there, but the donut probe is what's normally used for these, and it's kind of like a donut. It's got the hole in the middle. This is a Z-Tech probe. It's very heavy. Heavy probe usually means high penetrating power because there's lots of wires in the coil. The bigger the coil, the deeper the penetration that is possible. So for the test frequency on this one, what I have today, 5 kilohertz. And you know, when you're inspecting fasteners, protruding fastener heads, you're not inspecting the head really, you're inspecting the material that the fastener is connecting together. Or in the case of if somebody had a bad day and they forgot to put in a rivet, or if a rivet fell out, you'll also be able to tell that condition with your setup. So this is the ultimate case of pattern recognition. It's a very simple setup. You know, once you take your test procedure and you get the right test frequency, it's going to have you set the phase for a good fastener area to a certain setting like this. I happen to have this particular one set up like a smiley face, just for an example. And what we're looking for, and if you notice, I have my vertical gain set a little bit hotter than the horizontal gain. And if you can't read that, vertical gain is 65. Horizontal gain is 46. But you know, this is just an example of a good fastener right here. Now I'll find another good fastener. It'll be this one over here. Okay, so that's a good fastener. And then this next one will be a good fastener. And I'm going to go to one with an EDM notch, and you'll see that it's about a vertical division off of the normal fasteners. So just real quick, I'll hit 3 normal fasteners. There's 1, there's 2, there's 3, and then this next one. Of course, my display had to be erased, didn't it? So we'll do that one more time. One more time. Come on, erase. All right. There's a good one. There's a good one. That one, it's got a flaw. Now, I have a few other types of fasteners. Without resetting the phase. So this is a slightly different type of fastener without a notch. That one has a notch. So you can see there's about 2 vertical divisions difference. This is a good one. That's a bad one. And of course you could crank in a little bit more vertical gain if you wanted to see the separation even more, that's what I'm looking for, even more drastically. So now what I want to do is I'm going to switch over to a slightly different tester. This is going to be also a Nortec instrument. Now, just to show you that I go to great lengths to make these videos, both of these probes I'm using operate in the reflection or the driver pickup mode. So to run them with these 2 testers, I have to run the probe through an adapter. And to use this particular adapter, I had to make a special cable. But by doing all that extra work, I was able to come up with a configuration that would work for these videos. So for this example, I've just got a 2-layer sample that's got some fasteners. And it's kind of the same thing, right? Your procedure is going to have you calibrate in such a way that, okay, and I'm going to have to balance. Let's hit the balance button. You know, I don't really need 2 frequencies here, so let me go into the setup. Let me go into the setup, and let me go to single frequency mode. Okay, here we got 2 kilohertz. No, I could have used a slightly different frequency. This probe goes all the way down to 300 hertz. It's a smaller probe. All right, let's hit the old null button. Uh-oh, what happened? What happened to my tester? 2 kilohertz it didn't like for some reason. Uh-oh. Something's going on with my tester. 500 hertz, is that the one that was working well? Okay. Let me, 1 second, be patient. You always have to be patient with these videos. Okay. So, there we got a good fastener. There's a good fastener. There's a good fastener. There's a good fastener. Those are all good. That one's good. That one's good. That one has got an EDM notch. That would be this one right here. It's a crack between fasteners. Okay, so we got that one, good one. This donut probe barely fits around these fasteners, which is probably a good thing. So there's your bad one. You can see quite a bit of distance between the 2 flaws. So is there phase angle separation between those? You better believe it. Now, if this was a steam generator inspection or a heat exchanger inspection, you could imagine that each one of these signals is a tube support plate. Now, in a heat exchanger inspection on an absolute channel, we would have tube support plates rotated in this fashion. And if you were pulling your probe back at, let's just say 40 inches a second, every couple feet, you'd see one of these. Okay, you'd see one, then a second later, you'd see another one, then a second later, you'd see another one, then you'd see another one. You would see thousands and thousands of those signals in the course of a shift. We call those high repetition signals. High repetition signals aren't normally ones that we're interested in when we're doing eddy current tests, because high repetition signals are the ones that happen often. And in the case of heat exchangers, tube support plates are high repetition signals. Top of tube sheet expansions are high repetition signals. And in the case of fasteners on a large jumbo jet, fasteners are high repetition signals. So you're going to see lots and lots and lots of them. But since we are masters of pattern recognition in eddy current testing, let me change the angle on that one. We're going to set our fastener like that. And we're paying attention to the pattern, right? So there's a good one. There's a good one. There's a good one right there. There's another good one. There's another good one. Oh, whoa, is that one a bad one? So you might be inclined to say that there's a defect under that one, because that's a good one. And we just saw dozens and dozens, probably hundreds or even thousands of them. And then lo and behold, you get that one with a completely different phase. But here's an important point to note. Sorry about that. Just because it's different doesn't mean that you have a detrimental situation. Because let's look at the one right next to it. Ready? And wait for the screen to clear. That one looks just like it. And that one looks just like it too. So what we have there is just a case where we went to a different thickness, so there's more material there. So when you found that first one, you wouldn't want to start waving the red flag and saying, hey, I found a bad one, get the client over here and make a big ruckus out of it. Because he might say, you know, did you retest that area? And you'll say, yeah, it looks the same every time. And then the client might say, did you check the 10 rivets next to it? And you go, well, not yet. And you go, why don't you try that? Well, then you realize that all the rest of the ones in the continuation of that row have exactly the same phase. Now your client has lost confidence in your abilities, right? So if you think you find a flaw, always do retest. And if you see a shift in some sort of pattern, maybe you want to get the drawing, you know, or call your supervisor over and say, hey, I've noticed this shift in the patterns. Could this be something other than, you know, a defect? And the answer is of course, because in aircraft, you know, you're dealing with multiple layers and different kinds of fasteners and things like that. So things are going to be different, you know, over the cumulative body of the aircraft and the different components. But you just need to be careful to differentiate between flaws and geometry and different thicknesses of the material. All right, hope you enjoyed the video. Thanks for watching.